divide and conquer. There is no I in team. It was a group effort. There are more fancy slogans telling us how awesome teamwork is than I can count. Unfortunately, when you're taking a task that has traditionally been completed by one person and trying to turn that into a team project, it's not as easy as it sounds. Dividing up the tasks, delegating them, and managing the integration of all those parts can become a big, complicated mess. And you can end up taking even longer than if you just did the whole thing yourself. You then start to remember other phrases like, 9 women can't make a baby in 1 month. What? FPGA design is one of those things that's hard to split up. Without proper support in our tools and methodology, we can't easily turn an FPGA design project into a team effort. We need a design approach that supports team design from the ground up. Hi, I'm Amelia Dalton, host of Chalk Talk. Today's huge FPGAs cry out for team design methodologies. Nobody wants to design 2 million logic elements all by themselves. Luckily, Xilinx is one step ahead of us here. My guest today is David Dye, who will tell us how to design huge FPGAs easily with team design capabilities of Xilinx's latest design tools. Hi, David. Thank you so much for joining me today.
My pleasure. Glad to be here.
So, David, everybody talks about hierarchical design, but when talking to engineers, a lot of people don't seem to know how to use it effectively. What are we going to talk about today?
Well, what I'd like to cover today is an introduction to our listeners for the hierarchical design flows within the Xilinx ISE software. There are a few concepts I'd like to share regarding new approaches to synthesis and place and route that'll help them achieve repeatable results and faster design closure.
Okay.
I've got a few details for 2 of our hierarchical design flows, and I've also got a few considerations for successful application of these principles.
Great. So what is hierarchical design, and why would an FPGA designer want to use it?
Well, the purpose of hierarchical design is to allow the designers to break down the challenge of placing and routing a large or a complex design into smaller, more manageable pieces.
Ah, okay.
Divide and conquer.
Okay.
So our FPGAs are growing in size. Our large 7 series devices goes up to 2 million logic cells. Needless to say, the challenges that come with this progress has also grown. How do you manage such a large device?
Right.
Well, by using hierarchical design, you reduce the scale of the challenges, focusing on one part of the project at a time.
Ah, okay.
So what you want to do is meet your goals for these smaller pieces and then lock down those results. And by doing so, designers can significantly reduce the number of iterations through place and route. Even when you're making changes to some modules, preserved modules are not going to change, so you're not chasing down moving targets.
Ah.
So, for example, if you have a part of your design is a high-speed memory interface or a piece of time-critical IP like a PCIe core, you can use a partition to isolate its result. Once you achieve the goals of that particular module, any type of change to the rest of the design will not undo the validated results for that critical partition.
Ah, okay.
So hierarchical design within the Xilinx ISE tools represents a number of different solutions. Design preservation, team design, IP reuse, partial reconfiguration, and single-chip cryptography. All of these are variations on the base functionality established by partitions. But right now let's focus on the first 2, general design preservation and team design.
Okay. So how does someone approach design preservation, and how do those tools work?
Oh, okay, it's easy. As the name implies, hierarchical design requires partitioning the design based on its logical hierarchy. You'll see the best results when related logic and critical paths are grouped within a single bundle. So an example here, if I have a DMA controller that needs to have a tight connection to a memory module, put these 2 blocks together under a common level of hierarchy and place a partition on that level, as shown in green right here. These partitions can be evenly distributed throughout the design, or you could simply have one small partition on a particularly challenging block. The choice is yours. So then, once we've established the structure, when the implementation tools are run, the delineation of these group modules is maintained. Now, floor planning is not required for design preservation, but it can further direct the tools to place this related logic together. This is especially useful if it's expected that some of the modules will still see lots of changes. Floor planning would keep the modules from spreading out too much. Then during subsequent implementation runs, The unchanged modules are preserved. In this example, we've made a change to the CPU module, shown in red. The results of the top partition, as well as the data and control partitions, are literally copied and pasted from the prior run. Everything about these modules are preserved. Optimizations, placement, routing. Only the results of the modified CPU module are new.
Ah, okay. So you keep mentioning partitions. What are those? Is that a specific term in your software?
Yes, it is. Partitions are really the heart of the hierarchical design flows.
I see.
This is a matured technology, and it's a fundamental part of ISE. And recent changes and its inclusion in Plan Ahead has made it a more complete solution.
Ah.
So partitions are assigned to logical blocks within the design and represent everything about the results of that particular module.
Okay.
All this information can be completely reused, but there's flexibility as well. Users can select to reuse only placement, for example, and let the implementation tools reroute that part of the design. Now, we establish fences around these partitions, but they're soft barriers. We do permit some optimizations, such as constant pushing and unconnected port trimming, to still take place. Now, all these capabilities we're talking about are part of our current ISE software and support all of our current FPGA devices, including the 7 series. And partitions will also support Zinc, our processor-based platform, when the software for that family is released.
Okay, so David, are partitions easy to use? And how does one manage these hierarchical flows?
Well, we certainly think they're very easy to use. Well, all these flows can be run on the command line or via scripts.
Okay.
But a great way to use these tools is within Plan Ahead, our front-to-back design flow and project management environment. Plan Ahead gives you graphical control over all aspects of the hierarchical design flows.
Great.
As well as an interface to the Tickle engines. So within Plan Ahead, once you load in your design sources, your HDL, your EDIF, netlist, your IP, then you can define your partitions.
Okay.
So simply select a level of hierarchy in the RTL or a netlist view and choose Set Partition.
Okay.
Sounds easy. You can enable the boundary optimizations or other attributes to partitions. The import tag shown in this image shows that you can reuse a partition that was implemented in another design.
Oh.
Floor planning, pin placement, those are easily done within Plan Ahead. Design rule checks specifically written for hierarchical design flows are also incorporated into Plan Ahead, and you can run those at any time. Multiple synthesis and implementation runs can be managed from the flow window. Different options can be set for each run. When the runs are complete, you use the Promote Partitions window to control how these results are saved. Now, promoting a run for reuse saves a copy of that design and ensures that further iterations on that configuration doesn't overwrite your golden results.
Great.
Now, for later runs, the Specify Partitions window lets you pick which modules to reuse and from which prior run. And preservation levels can be set there. And finally, at any point, there are a host of analysis tools to let you examine results and check timing. Plan Ahead gives access to many integrated views of your design throughout the synthesis and implementation process.
So how does team design compare to design preservation? What's different?
That's a good question. Team design extends the capabilities of design preservation to support parallel processing. In a typical use case, this means that multiple team members can implement their portions of a design independently.
Oh, okay.
They can write new code, synthesize, run place and route, all without having the full design be complete or even present. Black boxes are used for missing partitions, and the tools understand that these partitions cannot be trimmed away. One difference from design preservation, though, is that floor planning is required. Now, given that these are independent place and route runs, it's important that when the results are brought back together, that they don't overlap.
Right.
Now, we call it team design, but this flow is not limited to multiple designers. This approach could be utilized by a single designer looking to run implementation passes in parallel.
I see.
You can run multiple partitions independently through place and route with different options much more quickly, and then assemble those independent pieces to meet your needs. So each parallel run will focus its attention on the specific partition being targeted, and this attention will allow you to close on requirements much more easily.
So David, can you show me what team design looks like?
Sure. Here's a design that targets a small Kintex 7 device.
Okay.
First, a team leader establishes the design structure, the hierarchy of the design, as well as the floor plan. In this image, top-level logic has been implemented, as you can see in blue, without any submodules and with no placement restrictions.
Okay.
Now, in this example, we're not going to save those results. Now, the team leader will then take the base project and pass it on to team members A and B, who add their own code to complete their modules.
Ah.
They implement their partitions in context of top with other modules set to be black boxes. Now in this case, team member A owns one module, as shown in yellow, and team member B owns two, the green and the pink. If other team member results are available, those can be imported to provide more context.
Oh, okay.
Now, once complete, or at regular intervals, the team members will promote their results to a central repository. The team leader then imports those results to assemble the full design. Now, as you can see in this final assembled image, the imported partitions for each team member are completely preserved, and then the implemented top-level logic is slightly different for each of these scenarios. Now, we've given priority to the submodule logic in the final design, and the top-level logic works around these imported modules.
Oh, okay.
The priority can also be flipped if the top-level logic is most critical. Team members can import a fixed result for top and have their modules implement with that context.
I see. This all sounds great, but this power and efficiency must come with a price, right?
Well, we certainly do have some rules and recommendations to get the most out of these flows. We've written the Hierarchical Design Methodology Guide to document these guidelines. Now, these are recommendations we suggest for all of our designers, but the effect of not abiding by them is a bit more pronounced when applying partitions. Now, the reason for this is simply that we need to keep everything in a partition logically together. We do allow for some basic optimizations, as I mentioned earlier, but full flattening of a design to perform global optimization is not permitted.
Oh, okay.
To minimize overhead and to obtain the best quality results, consider the guidelines shown in that guide. Here are 4 examples. First, register the partition boundaries, especially the outputs. This allows the tools to focus on the timing paths within a partition, avoiding combinatorial logic bottlenecks on the partition boundaries.
Right.
Another one is to keep critical paths within a partition. If a critical path passes through too many partitions, place and route tools may not have enough flexibility or visibility to optimize that path to meet timing.
Makes sense.
A third suggestion is to keep the number of unconnected or constant-driven ports to a minimum. This may be unavoidable for some IP, but it reduces the chances that dead logic may remain in your design results.
Okay.
And then finally, any logic that is best packed together should be kept in the same partition.
Right.
In this example here, if a block RAM sources a register, implementation tools will want to pull these together into a single site. Now, keep them in the same partition to make sure that that can happen.
That makes sense.
Well, so Amelia, I hope that you've seen how hierarchical design helps solve design challenges by breaking up large or complex designs into more manageable pieces.
Absolutely.
Using design preservation, you can greatly reduce the number of passes through place and route as you meet all your design goals. And by using team design, you can solve these challenges in parallel, further reducing your design cycle time.
Makes sense. So I'm ready to get started. Where would I go for more information?
Well, for more information, the best thing to do is to navigate to these 2 pages on Xilinx.com. Here you'll find the aforementioned Hierarchical Design Methodology Guide, alongside tutorials, white papers, and other documentation on these partition-based flows.
Fantastic.
Now, in addition, Xilinx hosts a forum where hierarchical design topics, among other things, are discussed. And we offer training courses that incorporate hierarchical design techniques in classes for plan ahead and partial reconfiguration.
Fantastic. Well, thank you so much for joining me today, David. It was a pleasure speaking with you.
Likewise. Thank you.
And before we go, don't forget to click that Download Now button below the player to download a free white paper that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.